Okay, I just got the recording started here on this, and I hope that I can start teaching now. Okay, so shall we start teaching if there's no question? Yes?
Yes.
Yes.
Okay, okay. So what I want to do is I'm going to quickly recap what we discussed last time. Again, one more check. You guys all see the stars on this side and this side, top of the blackboard?
Yes.
And the
Yes.
bottom here, left,
Yeah.
right? Okay, so that's the area I'm gonna write. So I don't want to write somewhere that no one can see. Okay, so we talked about vector calculus last week on Thursday. And the main thing that we used, and I try to remind everybody about that, was the component form of the vector algebra. And this is the type of vector algebra that we use a lot in electromagnetism, and especially this course. And as you get more professional in science and engineering, you will see that more and more people focus from other notations to component-based notations. Okay, so component-based notation means if we have any vector, vector A, depending on how many dimensions we are working, this can be written in terms of the components. Okay, if we are in 3 dimensions, A has 3 components, AX, AY, and AZ. And what is each of these components is the projection of the vector on that axis. Okay, so A can be written in terms of AX times X hat, which is a unit vector in the X direction, times Y hat, unit vector in the Y direction, and Z hat, which is a unit vector in the Z direction. Okay, so this is the general form that every single vector in whatever dimension we can write. If we are in 2 dimensions, it's going to be only X and Y. If we are in 4 dimensions, outside of the electromagnetic and mechanics, it happens, then we will have other components as well. Okay, so for this course, we are always limited in 4 dimensions, in 3 dimensions, okay? So then, very basic vector algebra using the components. If you multiply a scalar by a vector, okay, let's say A, small a times A, this one is a scalar, okay? This technically multiplies by each of the components. So that becomes A times AX times X hat, A times AY, Y hat, A times AZ, Z hat, and so on. Okay. Other type of vector operations, we had the dot product, which is actually becomes very easy and convenient using the vector notation. Imagine A is defined the way it is, and B is another vector that can be written in terms of BX X hat, BY Y hat, and BZ Z hat. Okay, so what is the dot product of A and B? I want you to answer.
It's the product of the magnitude of both vectors A and B times the angle cosine between them.
Yes, but if you want to use only the component form where we don't want to be worried about the directions and angle, how would the dot product can be explained written in terms of the components?
You have AX times BX plus AY times BY plus AZ plus
Times AZ. So
yeah.
technically you multiply the light components, right? You multiply the light components and add them up algebraically. The dot product, the outcome of the dot product is a scalar. So you just add them up, there is no direction associated with that, and it's gonna be a scalar. So it becomes AX BX plus AY BY plus AZ BZ. Sounds good? And then how about the magnitude of vector A in terms of the components? Here we are careful and we understand that these components, X, Y, and Z, are in Cartesian coordinate and they are always perpendicular to each other. And that's quite important, okay? You cannot define a random coordinate that you have unit vectors not being, okay, not being perpendicular to each other, okay? So here we are working in Cartesian coordinates, they are perpendicular to each other, and following that, we can write the magnitude of the vector in terms of the components, and that's going to be a square root of ax square, ay square, az square. Okay. How about the other product for the vectors? What was the other one? That was
Product.
Cross product.
Cross product, right? So there's a very different type of vector multiplication, which is A cross B. This is called cross product or sometimes vector product. And the reason sometimes called vector product is that the outcome of this is a vector, unlike the dot product where the outcome is just a number, okay? So the cross product using the angles and directions, we said it's, so if we have A here, if we have B here, the cross product is defined as A cross B being equal to magnitude of A, magnitude of B times cosine, times sine. Let me find my better eraser. Times sine of the angle between them, theta, and that is in the direction of n hat. N hat, we talked about this and we said we got to use our right-hand rule to find the direction of n. So in this case, A to B, n could be in this direction, which is perpendicular to both A and B, okay? And what we do is that we use our right hand, okay? We keep it in the direction of A, and then you move our fingers to the direction of B, okay, from A to B, and then we look at our thumb, which direction this thumb is showing, and that is the direction of the cross product, okay, something like this, okay? So this notation is using the magnitudes and using the direction, okay? It's more classical way of doing vector algebra. If you want to use component form, I introduce a matrix that the determinant of that matrix tells you the cross product, okay? And that matrix is set up as this. The first line are the unit vectors, x, y, and z. The next lines are the components of the first vector and then the second vector. So it becomes ax, ay, az divided, and then next line, bx, by, bz. Okay, if you want to expand this determinant, it's gonna have three terms. One of them x hat times the determinant of this matrix, this 2 by 2 matrix. The other one negative y hat, determinant of 2 by 2 matrix made up ax, az, bx, bz. And the third one, z hat times the determinant of these 2 by 2 matrix, which has ax, ay, bx, by. Okay, so everybody remembers determinant? Yes, okay. If you don't, just go back and take a look, okay, and refresh your mind about this. Okay, so these are the basic, very basic vector operations that we can do with components. And then beyond these, we also introduce two triple products. That means we have three vectors, we are multiplying them by each other, okay? And then if you learn these ones, and if you learn the triple products, any other type of higher order, more complicated vector products can somehow will be simplified into the form of either triple products or these type of products. Okay, so technically, if we know we understand these and we understand the triple products, we will be good doing all the vector algebra. It can be difficult, okay, that's a separate story. That can be difficult, but in terms of the fundamental information that we need to proceed with any vector algebra, these combined with triple products should be enough for us, okay? So we won't be doing too much complicated vector analysis, but at some points we do a little bit of involved stuff, especially when we are doing magnetism, not much in electrostatics, okay? So as we do this course from now until the end of the second semester of the course, you will use part of this, okay? So don't be nervous about these things, okay, if you don't feel comfortable, but be ready that we need to review these and use this, okay? And as we use this, you will get a lot more comfortable, okay? I can guarantee you finish this course, and after doing 2 electromagnetism courses, you feel a lot more comfortable with vector analysis, okay? So that's something that you learn on the side, okay? Any question?
Nope.
No? Okay, so I'm gonna quickly review the triple products as well, okay? And then we can move on to the new topics. Let me erase this. Nice. So 2 types, common types of triple products. The dot product of a matrix by the cross product of 2 other matrices like this, okay? And if you look at this, if I write in the component form, the first one, I can write it AX, X hat. AY, Y hat, AZZ hat. Okay, so this is the A, and we are doing the dot product of these by the second one is actually the determinant that I just told you guys, okay? So the second one is X hat, Y hat, Z hat here, and then we have BX, BY, BZ. We have CX, CY, CZ. Okay, and the dot product of this, if you look at this, here I said you will end up having 3 terms. One of them is X hat times determinant of this, Y hat determinant of this, and Z hat determinant of this matrix, okay? And then we have another vector AX, AY, AZ, each times the unit vectors being multiplied with the dot product, okay, with this, okay? So if you think about that, each like component needs to be multiplied, okay? And if that is the case, this whole combination, the product becomes like AX, AY, AZ. So the components sit here at the position of the unit vectors, and the next lines become BX, BY, BZ, CX, CX, CY, and CZ here. Okay, does it make sense? Yes, everybody?
Yes.
Good. Okay, and the other triple product we had was the cross product and the very famous back cap rule. Okay, so another way is, by the way, this triple product, you understand, the combination here is a scalar. Okay, B cross C is a vector, A is a vector, but A dot this vector becomes a scalar. Okay, so at the end we had that determinant, which is a single number. It's a scalar. And another triple product, I'm going to call that number 2, is the cross product of A cross B cross C. Okay, and this is very famous, known as back cap rule, which is what I do is that I always write back and then cap, okay, with negative sign, okay, and that is equal to vector B times A dot C, okay, minus C times A dot B. Okay, so the advantage of doing this, going from this one single term to these two terms, is that we are getting rid of two cross products. And you remember, cross product is sometimes hectic to work with, okay? Cross products are sometimes hectic, but the dot product is easy, okay? So here, of course, this is one term, and now we have two terms, so it doesn't look like it's very much simplified, but the fact that we are getting rid of the cross product and we are only using the dot product makes things easy, okay? So here, the outcome should be a vector, okay? And here what we have is A dot C. This is a scalar. Okay, this is scalar multiplied by the vector B. The combination is a vector. And here again, A dot B is a scalar. And multiplied by vector C, that becomes a vector, okay? And beyond this, we did one example last time that we had higher order multiplication, but we could kind of expand that and write that in terms of the triple products, and we could simplify that way. Okay, so I'm not going to repeat that example, and if there's no question, I'm going to move on to the next topics, which are position displacement vectors, and then we do more calculus, differential calculus. Okay, any questions so far? You guys good? Everyone's happy? Okay, nice.
Good.
Okay, so I'm going to erase everything, and I'm going to list the topics that I'm going to teach today. Okay, I'm going to start talking about the position and displacement, as well as separation vectors that we will be using very commonly in this course. And then I'm going to move on to gradients, define the del operator, we talk about divergence and curl. And hopefully we have enough time for doing all this today. Okay, so position vectors you should be very familiar with. And displacement vector, I think from mechanics you are familiar with. The way we use these vectors are actually interesting because a lot of times here in electromagnetism, what we are interested in is we have, let's say, a charge distribution, okay? We have certain charges and currents in space, let's say around here, around my left hand. And then we are interested in understanding what kind of field, electric and magnetic fields, these charge distribution produce here, okay? And another point, okay? So technically, we are in a three-dimensional space, okay? We are in a three-dimensional space. We have distribution of charges, and then we have, which are source, and then we have certain positions that are field point, and we want to see how these charges are creating that field. Okay, so what is interesting here is that the position of the charge is important, the position of the field is important, but what is the most important is the relative position between them, okay? So the notation that we use a lot in this course is that, let's say we have this system of coordinates, z, x, y, z, okay? And imagine we have one charge here, and I'm gonna call that source, okay? So it could be either electric charge moving or not moving, or a current at that point, okay? So at this point, I don't care about those details, but mathematically, I'm gonna say we have a source at this point, okay? And I have another point here that I'm gonna call that the field point. And that is where I'm interested in calculating the field created by this source, okay? So what happens is that, what if we have multiple sources, okay? We need to use a vector to explain the position of the source, and we need to use a vector to explain the position of the field point, okay? The common notation in this course is that for the source we use the prime notation, okay? So I say that position of the source is r prime, okay? Position of the field, where I'm interested in really calculating what force or field I have, okay? And for this, we use the non-prime notation, okay? So in practice, you will see a lot of r prime and r's throughout this course, okay? So I want you to be ready to always understand, if you have prime on top of anything, most likely it's referring to the position of the charges. And if we are referring to R, that is one point in a space, could be very, very far away from any charge distribution, but we are trying to calculate the magnitude and direction of the fields and so on, okay? So R prime in Cartesian coordinates can be broken down in terms of the x prime, x hat, plus y prime, y hat, plus z prime, z hat, okay? And likewise, R can be written in terms of x, x hat, plus y, y hat, plus z, z hat, okay? So very similar thing, but that prime is not only making a separate variable, it also will have a meaning and concept throughout this course. Okay, so if you look at other electromagnetic books, maybe they use different notation, but the Griffiths book, throughout the course, the notation is always like this. The prime notation refers to the position of the charge, and R non-prime notation refers to the position of the field point. Okay, so what is really the field a function of is not directly this, but is a function of a separation vector that use this form of R, okay? And that is R minus R prime, okay? And this is defined as separation vector. And that separation vector, if I use different line here, different color, This is the separation vector. And it should make sense, right? Because what if you move both source and field somewhere else? Are you changing the magnitude or anything about the field? No, because both of them are changing. So at the end, everything should be function of the separation vectors. Okay. And likewise, the magnitude of separation vector should be equal to the magnitude of r minus r prime. Okay. And sometimes we use the unit vector in the direction of the separation vector, and that should be r minus r prime or over r minus r prime. Okay, so this is the magnitude. And this is the unit vector. Sounds good? Any question?
What is the sword in the field point?
Okay, a lot of times here we have a charge or current distribution, and we are interested in finding what kind of field those charges are creating. Okay.
Okay.
So wherever you have a charge, we call it a source.
Oh, gotcha.
And wherever in a space that we are calculating what electric field we have, we call that a field point. Okay.
Gotcha.
So you can imagine here we have one or even multiple charges. And here, technically, we have nothing, but we want to calculate what electric field is created there, or magnetic field.
Gotcha. Thank you.
Okay. All right. So that's it about the position displacement vectors. And then I'm going to move on to differential calculus. Okay. Everybody knows what gradient is? Okay. Let's start from very basic, simple derivative, right? Imagine we have a function f(x). Okay. So this is a function of x, and we have x here. Okay. And let's say it has a very nice behavior like this. Okay. So sometimes we are interested in finding what is a very infinitesimal change in f as a function of change in x. Okay. Imagine this is a function that shows a speed, or let's say position, as a function of x. Okay. And then you want to change x a little bit, and you want to see how much the function is changing. Okay. So you know this infinitesimal difference in f, we show it with df, okay, and a corresponding change on the x-axis, that is dx, right? So relationship between df and dx, you know that df should be the slope of the curve at this point, right? The slope at this point times dx, okay? And that is the trivial relationship between in a curve where the change is very small. We are technically approximating it with a simple line, okay? And now what is the slope here? Here is the definition of the slope being df over dx, and this is the derivative. Okay, so df.dx times dx, and that is the infinitesimal change in df we have. Okay, so this is very nice, simple for one-dimensional function. Okay, and The gradient is actually similar concept, and I would say exactly the same concept, but in 3 dimensions, okay? Now consider a function similar to f(x), a scalar function, okay? But the only difference is that the other function that we have, let's say this is the function of 3 variables. Let's say t being function of x, y, and z, okay? And this is 3-dimensional function. This was 1-dimensional function. How do we map the same concept on a 3-dimensional vector? Okay, 3-dimensional function. Okay, so that's where the gradient comes into use. Okay, so can you tell me one sample of a function in physics that can be function of 3 variables? Can you imagine anything? And by the way, this is a scalar function, right? It's not a vector. It's
like let's say I guess the magnitude of like a field.
Magnitude of the field, yes, that can be. Magnitude of the field is not used very commonly.
Yeah, that was
because if you have a vector field, then you have vector field, okay? Yeah. But we have a lot of scalar functions, okay? In this course, electrostatic potential is a scalar function, okay? And more simple scalar function that you can think of, and that's actually an example from your book, is temperature, right? I'm standing here in this room, okay? The temperature, I feel is constant, but you know what? If I get closer to the door, it's a little colder. If I get closer to the window, it becomes warm because sunshine is coming in, okay? So technically, you can define the temperature in my office as a 3-dimensional function. It's a 3-dimensional space, x, y, and z. And hypothetically, you can imagine I have imagine I have a thermometer in my hand, and that reads very quick, very fast. If I move that thermometer, I have different readings, right? So that is technically a 3-dimensional function, which is a function of position, function of x, y, z, and I move that and I read that number, okay? That's a completely 3-dimensional, that's a scalar function, being function of 3 variables, okay? So this could be very well the temperature in my office, and x, y, z is the position that I have the thermometer in my hand. Okay, so something like that. Now, the question is this. I have this thermometer in my hand. I make a very small move, okay? So it could be in x, could be in y, could be in z, or in combination of them, okay? Doesn't matter, as long as it's very small move. What do you expect? Most likely temperature is going to change. Is it going to change a lot? Probably not, right? Because I'm making very small move, temperature is going to move very little, okay? So the function t, we want to find a way to write the change in the temperature as a function of the motion ID, okay? There should be a way to write how much temperature change, small changes by the way, how much temperature change in terms of how much and what direction I moved my hand, okay? So we want to do that, okay? So mathematically what we can do is, let me get rid of this. Mathematically, there's a partial derivative theorem that says if you have small changes in such function like t, that could be written in terms of the small move that you make. Okay, a small move, what does it mean? That means we are in 3-dimensional space. I make a move of like dx times x hat plus dy times y hat plus dz times z hat. Okay, so this is technically a small move. It has x component, y component, z component. It has all 3 components, but in each direction, the move is very small, okay? And as a vector, we can actually write it in terms of dl, okay? So a small, infinitesimal move in space. And then t is changing, okay? Purely mathematical, okay? Forget about space and 3-dimension. The theory of partial derivatives says that if t is a function of these 3 variables, any change should be equal to the partial derivative of t with respect to x times dx plus the partial derivative of t with respect to y times dy plus the partial derivative of t with respect to z times dz. Okay, so this comes from the partial derivative theorem. Okay, t is a function of three variables. Okay, and a small change in this should be this derivative times dx, this derivative times dy, and this derivative times dz. Okay, this is just mathematical definition of the partial derivative. Okay, now if we look at this, and if we look at this vector, there is another way that I can write this dt, which can first look more complicated, but then eventually you will see that's actually very helpful. Okay, so what I want to do is that I want to write the same thing, the same three terms that I have here in the form of a dot product. Okay, so what I want to do is that I want to write dt being equal to, open parentheses, I want to say x hat times dt over dx plus y hat dt over dy plus z hat dt over dz. Okay, so this is now a vector that I want to multiply by another vector, which is dx x hat plus dy y hat plus dz z hat. Okay, so this is a vector, this is also a vector. And this is a dot product. Okay, so if you look at this dot product, what you do is that you multiply the like components and add them algebraically. Okay, so dt over dx times dx, dt over dy times dy, dt over dz times dz. Okay, so these two terms combined with these dot products is actually the same as what we have on the top. Okay, so in a way, I just expanded that and I wrote it in a way that it looks more complicated, okay? But now, if you look at this one is exactly the displacement I have here, right? The second vector here is dl, okay? And the first one here, I want to define it as a gradient, okay? So the whole thing here, I want to give it a definition like this and say this is the gradient of t. Okay, so for any field, a scalar field, this definition, okay, is equal to the gradient of t, and that should be equal dt. Okay, and this form of notation is very common, and this is the definition of the gradient, actually. Okay, so what we have here, t is a scalar vector, is a scalar function, okay? T is a scalar function, like the temperature in my office. And the gradient of the t is partial derivative with respect to each component, each direction, times the unit vector in that component, okay? So gradient of t combined is a vector, okay? Again, t itself is a scalar, but the gradient is a vector, okay? And the way it's related to each component is written is just partial derivative in each of them, okay? So if we have two-dimensional function, we only have x and y. If we are three-dimensional function, we have x, y, and z. If we are in one dimension, okay, everything becomes the simple example that I started with, because you only have one single direction, and that becomes partial derivative with respect to x. And if it's one-dimensional function, you don't need even to say partial derivative, you just say the derivative, okay? So in one dimension, the whole thing boils down to what I started with in terms of fx and x. Make sense? Is it clear?
Yep, perfectly clear.
Any question?
What is DL again?
dl is a very small change in the position in a space.
Okay. Okay.
I have a question. So,
Sure.
so before dt was just a, well, I'm just kind of confused with the notation. I want to make sure that
Sure,
dt
yeah,
is,
yes.
is either
That's the
is
purpose
either
of asking question. Don't be shy.
is either a vector or something else, because when you gave the definition of dt, it didn't have the unit vectors x, y, and z.
Okay, let me figure out. D, you mean this sort of dx or?
The one on top, dt equal to, yeah,
This
that,
one.
yeah. I'm
Okay.
just asking
So
why.
this is a small change in. Let's go by example. Okay, I said temperature in my office. Okay, and if I have a thermometer in my hand and move that a little bit, I see a little bit of change in the temperature. Okay, so dt refers to that little bit of change in the temperature. And dx, dy, dz are change in the position. That created the change in the temperature. Am I answering your question?
Yeah, yeah, I get it now. I get it now.
Okay, good. Thanks for asking. Cool. So, so this is the definition of the gradient, which is exactly like this, okay, and it's always like that. What is the concept of the gradient? Now, conceptually, how do you think about the gradient? When we talk about the derivative, what's the first thing that comes to your mind? Let's say derivative of a one-dimensional function. Is it a slope? Technically, that should be, okay. Going back to the initial example, if we have fx as a function of x, okay, if we have this, if I say derivative at this point, the first thing that comes to your mind, I want that to be the slope here. If I say derivative is positive, I want you to quickly understand, okay, derivative positive, it's increasing. If I say derivative is negative, that means it's going down. Okay, so that's the type of thing I want that quickly come to your mind. Okay, so now what about the gradient? Gradient is technically multi-dimensional. Okay, and that makes it a little different. Okay, but still I want you to have a good intuition of what the gradient means. Okay, and for that I want to give you one example. Okay, imagine you are standing on a hillside. Okay, and not exactly on top of the hill, but somewhere that has a slope. Okay, if you are on a hillside, you can stand and then you can look around 360 degrees and look at the different direction. Okay, I can say that there is one direction that you will see the slope is maximal. Okay, that means if you walk forward, you're going to move down with high slope. And if you move backward, you're going to go up. Okay, so that's the direction with very high slope. On the other hand, for every hill, okay, if it's smooth but having a slope, there's always one direction that you can move and you won't see actually any slope. That means you move, but your height does not change, okay? So it could be, if I'm looking at the direction that with the highest slope, it could be like this. If I move left or if I move right, my height does not change, okay? That's technically what it may look like if you're on it, okay? But if you move forward and backward, then you will feel the highest slope, okay? So hill, okay, is technically a two-dimensional function, okay? For any hill, you can write it in terms of h of x and y, and this is the height, and this is xy position, something like that, okay? So gradient of h, gradient of the hill, is a vector in the direction that you will feel the highest slope, the highest change, okay? So gradient for any function, for any scalar function, tells you the magnitude and a direction, okay? What is that direction? That direction is a direction that you feel the highest slope, okay? And the magnitude of that is gonna tell you what is that slope, okay? Make sense? I have a chat message here. Yes, direction of the greatest change. Thank you, Josh. That was correct. Okay. So, so yeah, that's a concept. Okay. Does it make sense for you guys?
Yes.
Okay. So going back to the example with the thermometer and the position of that thermometer in my office. So if I look at the gradient of T, okay, the gradient of T is, let's say here, okay. I have the XYZ, I have the temperature, and now I calculate the gradient of T, okay. The first thing, the gradient is a vector, okay. So that has direction and that has magnitude. So you can sort of imagine that the marker in my hand is a gradient, okay. The gradient is not a scalar anymore. So at this point, I calculate the gradient of T, and it becomes like this, okay. Direction and magnitude. That means if that thermometer in my hand, if move it in that direction, I will see the maximum change in the direction that is positive, okay? And that means also if I move exactly opposite direction, I will see the maximum change, and that I will see a drop in temperature, okay? And at any point in a space, you can calculate gradient, okay? I can come here and calculate gradient. It might move, show in this direction. That means if I move in that direction, I will see increase in the temperature, and that's the direction that I will see the maximum increase right at this point. Is it helping?
Yes.
Okay, good. Okay, so we define the gradient like this, but this inverted triangle operator is used very often and also for different purposes than gradient in vector calculus, okay? And that's really, really helpful, okay? So what people did, they defined this inverted triangle called del operator as a del operator, and then from that operator, they defined other functions as well, okay? So starting from the gradient, let me erase everything else, but leave the basic definition. Let's get to it. Okay, so this is basically the gradient of T here. Okay, so we got this, okay, and from that people define this, the del operator as x time, x hat times T over dx plus y times T over dy plus z times D over dz. Okay, so this is an operator defined like this, and this is a vector operator. Okay, so I will always use arrow on top of this. Okay, and these can operate on vector fields as well as scalar fields. Okay, so the gradient was technically this operator acting on a scalar field. Okay, so what it has is that it has three terms. One of them is, for all the terms, the first component is a unit vector in one direction, and the second one is just a partial derivative, okay? So partial derivative of what? Here, it depends on what this vector is acting on, okay? If it's a, if it's acting on a scalar vector, is going to be exactly what the last example was, okay? So technically, if it works on T, then the partial derivative works on T, T, and T. Okay, so here it's not x component of t, this is just the t, the scalar function at a specific position, and the same thing happens here. Okay, so this is how this operator works on a scalar field. Okay, but then we can use very similar way and use this on vector fields as well. Okay, and the way you can think about this is this: the vectors, we can multiply that by scalars and vectors, right? So I'm gonna separate these, and just for the analogy between the del operator and regular vectors, I'm gonna give you example. Like if you have vector A, okay, you can multiply the vector by a scalar, okay? And that means every component is being multiplied by a scalar, like ax times a plus ay times a plus az times a. Okay, is it legible what I wrote here? Okay, so this is simple vector and vector multiplied by a scalar. Okay, so very similar thing. We have vector operator, and this time vector operator acted on a scalar, and then we have everything multiplied by t. Okay, but there are other ways you can multiply vector. You can, let's say, you can do the dot product of a dot b. Okay, and you can do the same thing with the del operator. Okay, imagine we have a field that is not a scalar field. Imagine it's a vector field. Okay, and let me get rid of this. And imagine we have a field of, let's say, v being vx times x hat plus vy times y hat plus vz times z hat, and this is a vector field. Okay. Okay. We can use the del operator on a vector field two different ways. One of them is a dot product. We can do the del operator dot v, okay, and this is technically the definition of the divergence, okay, and this is going to be the del operator, the x component of this acting on x component of this, okay, so it becomes dv partial vx over x plus partial vy over y and plus partial vz over z. Okay, and because it's a dot product, we add the like components act on each other, and we add them algebraically. Okay, so the outcome of this, the combination, is a scalar. Okay, this is one way. And another way of using the del operator, okay, I'm going to continue here, is acting using the cross product. Okay, so del cross v, okay, and for this one, we need to use the determinant, x hat, y hat, z hat, okay, and the first line becomes the partial derivatives, d over dx, d dy, d dz, and then we have vx, vy, vz. Okay, so this is the cross product. This dot product of the del operator by a matrix is called divergence. This one is called the curl. Okay, so next I'm going to look at the divergence and curl in more details. Okay, but the basic definition of these is that we have the del operator, which is a vector operator, and we act them on a vector field. If we do the dot product, the outcome is a scalar vector, the derivatives in each component, add them algebraically, and the cross product is a vector like this. The outcome is actually a vector, and this is how we can find this vector. Okay, Does it make sense how we moved from definition of the gradient to the del operator and then how define the curl and divergence? Okay, so the concept of the gradient for me is the very basic concept for defining the del operator, okay? But then once the del operator is defined, that can be also used against vector fields as well, okay? So technically I've covered these two. And the next I'm gonna look into the divergence more closely. Any questions so far?
What were you explaining on the right corner? On the right top?
Right up. Okay, I was saying that the same way that we can use vectors and apply them on scalars or other matrices, other vectors like dot or cross, the del operator can be acting on scalars or can be acting on vectors with dot product or vectors with cross product.
Okay, gotcha. Thank you.
Okay. So in a way, I was trying to say that the way we use the del product is somehow similar to the way we use the actual vectors. Okay, we multiply by scalars, multiply by vectors, and we do cross product by vectors. Okay. Any more question?
Yeah, you mentioned the curl will give a vector, right?
The curl give a vector, yes.
Thank you.
Okay. So I'm gonna erase everything and then focus more on the divergence now.
Does when you multiply the del operator times a scalar, does that give you anything, or it's just you know how like the other ones give you divergence and curl?
Yes.
It
So
would be
del
like
operator working on a scalar becomes gradient.
Okay. Oh, gotcha. Okay.
Yeah. Okay. So what is the meaning of divergence? The name and actually the divergence, it's a good name. What does it turn on in your head as soon as you see divergence? You hear divergence. Something is diverging, okay? And in terms of knowing that divergence is defined on vector fields, okay, so probably it's talking about certain fields with the field lines not moving straight in one direction or the other, probably the field lines that either originating from one source and diverging from that to the space. Okay, so that's actually the meaning of divergence. And this is very interesting in electrostatics because we always have point charges or distribution of charges, and each point charge, okay, in a way creates a field that is diverging in space. Okay, so as soon as we have some charges, okay, the divergence at that point becomes non-zero. Okay, if there's no charges, divergence becomes zero. Okay, so this is the concept that we use a lot in electromagnetism. Okay, so let's go by example. Okay, and then we see what we can calculate by divergence and how that is related to the concept of the vector field diverging. Okay, so I'm going to look at two vector fields. Okay, so I'm going to define two vector fields, and for both of them, I want to calculate the divergence. Okay, so number one here, I want to draw a vector field that looks pretty much like this. Okay. So imagine we have a vector field like this. Okay. So mathematically, this vector field can be defined as B being x times x hat plus y times y hat plus z times z hat. Okay. And that means at every position in a space, we have a vector, and that vector has the components, the x component is equal to the position of x, the y component equal to the position of y, and likewise for the z component, okay? So if you go further from origin, you will have a vector that is increasing in terms of values because you're going further from origin, your x, y, z values are increasing, so the vector is also increasing, okay? So if you go one step further, you're gonna have a longer vector field and a stronger vector field, okay? So this is a mathematical definition of this vector field, and this looks like this if you want to visualize that using arrows, okay? So now, you clearly visually see something is diverging, right? Okay, let's calculate divergence for this, okay? So the divergence of V is partial derivative of the x component with respect to x. So that means partial derivative of x with respect to x plus partial derivative of y component with respect to y, and that is dy dy. Likewise for the z component, we get partial over z, and each of them is actually 1. 1 plus 1 plus 1, and that is 3, okay? So we had this vector field, we calculated the divergence and become 3, a positive number, okay? That means at every point in a space, something is diverging, okay? And wherever you are, okay, you have these vector fields, okay, and that's sort of diverging from one origin, okay? So this type of vector field has a positive divergence. Any question?
Yeah, I do.
Sure.
When you say something is diverging at any point in space, what is diverging? Is it like a force or?
This is a field, it's all about the field points, okay? So at every point in a space, okay, you have fields, okay? And then you can move your position in space, and then you can see in what direction the field lines are changing, okay? So if you move a little bit left, right, up and down at any point and associate one vector field to each side of a cube like this, okay, and then look at those field lines, you can sort of get idea if anything is diverging or not diverging. Okay.
So
but in terms of the value, whether anything is diverging or not, is actually, you should calculate this divergence and see what you get at the end. Some of the vector fields, visually, it doesn't look like anything diverging. I will give you one example, but actually there is a divergence associated with that.
Okay, thank you.
I guess the origin of this is very clear because you have all these fields pointing on differently, okay? But at other point, the same thing is happening in the sense that if you move a little more away from your position, you're gonna get a stronger field moving away. Whereas if you're closer to the origin, you get less strong field going away.
So as far as the divergence, there's nothing special about the center of that in that particular case?
There is nothing special about the center for this specific because always the divergence is a constant, and that is 3, okay? For a lot of cases, the divergence, we have fields and use that in electrostatics a lot, that we have the field diverging, and the way it diverges is that we get divergence being infinitely big right at the center and 0 at the rest. That is still a diverging field, but it's not distributed nicely. It's super strong at the center and then not as strong at the rest of the land. Okay. And by the way, that is the field created by the point charge. That's how it is. If it's really, really tiny, tiny point charge, you have infinite value of the divergence right at the middle, and then everything vanishes.
So physically, what is the constant mean?
Okay, I got one question. Doesn't that converge to a point? Negative divergence is convergence. Okay, we could have a field like this, all the arrows pointing to the center, okay, and having negative x, negative y, and negative z here, with a divergence being -3. Okay, so convergence is just one type of divergence with negative sign, if that makes sense.
Yeah, actually the question that I was gonna ask you is what does the number 3 represent physically? Now that we're talking about a.
Can you please repeat what does number 3 represent?
Yeah.
I cannot say what is 3 versus 4. Okay, these are all the value of divergence. But if it's positive number, that means you have fields that are diverging in a way that if you go further from the field, you get a stronger. If you go further from the origin, you get a stronger field in that sense. And how stronger depends on 3. Okay. Imagine I had here 2x, 2y, 2z, right? Instead of x, y, and z. Just a bit stronger field. I would have get 6 here. So in a way that shows the strength. That shows how fast it's diverging.
Oh, so it's just how fast you're diverging from the point?
Yeah.
Okay, thank you.
Sounds good. Any more question?
Were we like doing it at a specific point, like, or is this for the whole thing?
So this is for the whole thing. Okay, so
gotcha.
the divergence is a scalar. Okay, here it turns out to be constant, but it's a scalar field. Okay, so the divergence is defined for any point in the space. Okay, if I want to change this example a little bit, I can say instead of x, I have x to the power of 2, y to the power of 2, and z to the power of 2. Okay, that makes things a little more complicated because it's x to the power of 2. Each of these derivatives here, I get, instead of 1, I get 2x. Okay, and here I get 2x as well, 2y, and then I get 2z. Okay, and for any point, this is not 3 anymore. Okay, so at any point in the positive x and y and z, it's positive number. Okay, it's not a constant. Okay, it depends on the position. If you're in the positive directions of the x, y, z, it's a positive number, and that's diverging at that area. Okay. So this is a scalar field. It has x, y, z. It should be dependent on x, y, z. A special case, it became constant, but that doesn't mean it's a constant number. Sounds good? Okay, we are out of time. I want to quickly tell you that you can repeat calculating divergence, okay, by looking at a field that is a constant field in a space, okay? The very simple scenario mathematical definition of having a constant field is V being equal to a constant, let's say 4, just number 4 times, let's say, Z hat, okay? This is a field that is showing a constant field, okay, in all space. You move in a space, nothing changes. Your field is always number 4 times Z hat, okay? And for this, if you look at the divergence, okay, I believe it makes sense, nothing is diverging, everything is constant, but if you calculate the divergence, what you get is the partial derivatives here, and all of them become 0, so divergence is 0, okay? And now if we change it a little bit and make this dependent on z position, we actually get a non-zero divergence. On Thursday, I'm going to recap this and then move on to curl as well. So I'm going to again talk about this so that the concept becomes clear, and then we talk about curl as well. Okay, so we are out of time. I don't want to go too much out of time. Okay, sounds good. Any question? Okay. Again, I want to remind everyone, please, if you got the invitation from Kriti, go there and register. If you don't see any invitation, please send me an email so that I can re-invite you, and then we make sure that by Thursday, everybody is in the platform. We do a run test. Sounds good? All right, guys, everyone have a nice day, and let's stay in touch.
Great, thank you.
Okay,
you.
thank you.
Thank you,
Bye.
Professor.
Have a good day.